Hello everybody and welcome back to another Big Ideas Algebra 2 lesson. Today we're talking about section 4.6, the fundamental theorem of algebra. It's a pretty bold statement. Something is so fundamental. There are fundamental theorems for just about every subset of math. There's a fundamental theorem of calculus and geometry, and it's basically another way of just saying that this is something that's very important to keep in mind, though not necessarily difficult to understand. Let's take a look at this table here. I've given you a whole bunch of equations on this side, and I've just told you the degrees of them. As a reminder, the degree is the number of variables on your leading term. As we look through, I've also written down the solutions when we solve for x. So in this one, we could add 1 to both sides, divide by 2, we get x is 1/2. That's just one solution. To solve this one, we would end up getting plus or minus the square root of 2. So that's two different solutions. Over on this trinomial, we can actually use the AC method to factor this, and we would end up getting that x is -3 and x is -2/3. Another two solutions. We can go through and we can find different solutions to all of these equations. But there is a pattern that we might start to notice. For a degree 1 polynomial, where there's only one x, you're only going to get one solution. As soon as you get a degree 2 polynomial, look at the number of solutions we get. We end up having two solutions, two x's that we want to find. If we have a degree 3 polynomial, meaning x cubed is your biggest, we end up with a possible 3 solutions, even though in this one we have a couple of repeated roots. What's going on here? Well, what's going on here is we have discovered something very fundamental about algebra in general. Here is the fundamental theorem of algebra. You don't need to memorize it, but if f of x is a polynomial of degree n, then the equation has at least one solution. As long as you have a polynomial where your degree is positive, yeah, you end up with at least one solution. There's something that's correlated with this, which is even more important. If you have a polynomial of degree n, once again, it has exactly n solutions, provided that the solutions that are repeated are counted twice. Depending on what degree your polynomial is, that's the number of solutions you get. So this is a great guideline for helping you to solve these crazy looking polynomials. It can be complicated when you look at a polynomial and just ask, okay, how many solutions are there? But once you start to see this rule, you can start to tell exactly how many there are. Like for instance, in example 1, we can look at the degree of this first term here and say, okay, how many zeros are there? Well, the degree is 3, so there are 3 zeros. There are 3 answers, because that's the degree of the polynomial. And it makes sense, right? In order to get an x cubed, that's x times x times x. An unknown times an unknown times an unknown. So, yeah, there are going to be 3 answers to this. To find the solutions, of course, this is where we need to use our solving methods. My recommendation is this. Check to see if you can factor it first. If you can't factor it, you might have to go back to the rational root theorem from section 4.5. Can this be factored? Well, when you have 4 terms, the way we try and check if it can be factored is by grouping. So let's group these together and see what we can pull out. What do the first 2 terms have in common? They have an x squared in common. And if we take out an x squared, x cubed divided by x squared is just x. 3x squared divided by x squared is just 3. Let's see what we can factor out of these groups. Both of them can be divided by 16. So we put a plus 16 here. we end up with x plus 3. How do I know this is factored correctly? Well, when you factor by grouping, you know you've done it correctly when these two groups match. If they don't match, it means you can't factor by grouping, unfortunately. It means you might need to do something else. But looks like we did it 100% perfectly. So our two factors are x squared plus 16 times x plus 3. Perfect. Now, remember that if we're trying to solve this, we should set these equal to 0. If we want to figure out what each solution is, we should set it equal to 0, then set each piece equal to 0 and solve. So we want to set x squared plus 16 is equal to 0 and solve. And we want to set x plus 3 equal to 0 and solve. Good news is x plus 3 equal to 0. That's an easy one. We can subtract 3 from both sides, giving us x equals negative 3. One of our answers is negative 3. The problem is, this one's a little bit trickier. We have to think, how can we solve this? We can't factor it because it's not a difference of two squares. Let's try using the square roots method. So we can solve by taking square roots, just like we've been doing for 2 units now. Getting the x closer to being by itself, square rooting both sides. The square root of x squared is x. The square root of negative 16, that's going to be imaginary. We know that we can't take the square root of a negative, so we can pull out the letter I and have the square root of 16 next to it. Well, the square root of 16 is 4. Don't forget your plus and minus. See, I forgot it. The square root of 16 is 4, so this is plus and minus 4i. Therefore, our three zeros are negative 3, positive 4i, and negative 4i. All we're doing is we're using the solving methods we know. Now, this one here is going to be a little bit trickier. First off, how many zeros are there? The highest degree is 4, so there are 4 zeros. There are 4 answers to this problem. The degree tells you how many answers there are. Is there something we can factor out from this? Yes, we can factor out an x. See how every term has an x in it? Let's take out the x and put the rest in parentheses. Oops, so this will be x to the third plus 6x squared plus 12x plus 8. And we can now see how we can solve this. Let's start off by seeing if we can group it. So let's try it out. If I try to group this, I would end up with x times the group of x cubed plus 6x squared plus the group of 12x plus 8. What can I take out from the first group? Well, the first group has an x squared in common, so I can take out x squared and just be left with x plus 6. Don't worry about the type of brackets I'm using. I'm just using these different types of brackets to distinguish. It's nothing fancy. And what can I take out of these two? Well, both 12 and 8 can be divided by 4. So we get 4x plus 2. Did we successfully factor by grouping? We did not successfully factor this by grouping. Why? Why did this not work? Well, it didn't work because the groups aren't the same. You see how in this problem it was both x plus 3? This other group, it doesn't work that same way. So what on earth does that mean? Well, what it means is we'll have to use a different method. It means that factoring by grouping was not the way. So I'm going to cross this off because this was not the way to solve it. This is not solvable by factoring. Well, if it can't be factored, what can we do? Let's start back where we left off. Let's start at x times x cubed plus 6x squared plus 12x plus 8. And again, we're trying to solve this, so we can set it equal to 0 if we want. I'm going to save it till the end. How on earth can we solve this if we can't factor it? Well, in 4.5, we learned a method to do so. Let me flip over to 4.5 real quick to give you a quick refresher. In section 4.5, we learned a little thing called the rational root theorem that says every factor, if you want to factor a polynomial, every possible factor is of the form p, where p is a factor of your constant term, divided by q, where q is your leading coefficient. In order to use this fact, we should first figure out what all the different solutions are of the polynomial, list them out, then, one by one, try them out. It's going to take some elbow grease, but I think we will make it there. Especially because the numbers we have here are kind of nice for this. Here, we have a constant term of 8 and a leading coefficient of 1. So, all the solutions of this polynomial, all the different answers, p over q, can be written as all the factors of 8, or all the things that multiply together to make 8, divided by all the things that multiply together to make 1. There's only two numbers that can multiply to make 1, and that's positive 1 times positive 1, negative 1 times negative 1. To multiply to get 8, you could do 1 times 8, or you could do 2 times 4. Just don't forget the plus or minus signs. So, all of our different solutions, the different answers to this polynomial, are as follows. Positive or negative 1, positive or negative 2, positive or negative 4, positive or negative 8. These are all the solutions to this one right here, or all the real solutions at least. We need to use synthetic division to test these out. So, first things first. Let's start off with the basics. Let's start off at 1. As a reminder, what this means is we are going to divide this polynomial here by x minus 1 and see if we get something that works. This is how we test if x minus 1 is a factor. So let's write down all the coefficients. This is 1x cubed, so we write it as 1. This is 6x squared, so we write it as 6. This is 12x, so we write it as 12. And this is 8. We just leave it as 8. Now what we need to do is fill in the rest of this table. Let's do the synthetic division, everybody. So, we take down the 1, and we multiply it by the term 1. And 1 times 1 is just 1. So I put a 1 here. What's 6 plus 1? 6 plus 1 is 7. 7 times 1 is 7. 12 plus 7 is 19. 19 times 1 is 19. And 8 plus 19 is 27. What does this mean? It means that if we were to divide this polynomial by x minus 1, we would get our x minus 1 times 1x squared plus 7x plus 19 plus a remainder of 27 over x minus 1. We don't want a remainder. We want to see what can factor this perfectly. So that has just told us that 1 is not one of our solutions. We have gotten rid of one of the possibilities. It's not positive 1. Pause the video and try the next couple of synthetic divisions. I'll let you know it won't take you too long. Try the next couple synthetic divisions and see if you end up with 0 as your remainder. If you end up with 0, it means that x minus whatever your number was is a factor. Pause it and try them now. How'd you do? As you go through, -1 doesn't work. 1 is your last term. 2 doesn't work. 64 is your last term. But look at what we end up with at the end when we try out -2. -2 works. We end up with a 0. So what does this mean for our polynomial? It means we can factor this polynomial with x minus -2. And we can just write this, instead of minus and negative, as x plus 2, remember? So we can factor our big polynomial here as the following. We have our x hanging out in the front. We have our x plus 2 that we just divided by. And then we have whatever we're left with. Remember that this is your constant term, this is your x term, and this is your x squared term. 1x squared plus 4x plus 4 is what we're left with. We're so close to being done with this problem. The last thing we need to do is figure out how to factor this and then set it all equal to 0. And I've got some good news for you. This can be factored using a combinator or one of your special patterns, if you remember the special patterns. I'm going to show you the special pattern. The special pattern here is, this is called the perfect square trinomial. Remember, the key is if your first is a perfect square, the last is a perfect square, and the middle is 1/2 of your last term squared, you got it. It's a perfect square trinomial. So we can factor this as square root of the first plus the square root of the last, so x plus 2 squared. If you really wanted to simplify this problem out, you could write it as x times x plus 2. And since this is x plus 2 squared, and there's another x plus 2, you could say this is x plus 2 cubed. That'll equal 0. Now, to actually solve this, we want to set each piece equal to 0. Remember that all the way back at the start of the problem, we discussed how many solutions we wanted there to be. There should be 4 solutions here. There should be 4 zeros. So if we end up with x times x plus 2 cubed equals 0, how do we get 4 solutions out of this? We set each piece equal to 0, even the ones that repeat. X cubed is just, or x plus 2 cubed is x plus 2 times x plus 2 times x plus 2. So if we set each piece equal to 0, well, here we get 0. To make x plus 2 equal to 0, x has to be -2, -2, -2. These are 4 zeros. Our 4 solutions are 0, -2, -2, and -2. Done. Those are the solutions, 0 and -2. Let's flip the page, everybody. These are some extra practice. These will involve some complex numbers. I'm going to write down the answers to these in just a second for you to copy down and try out on your own. But the complex conjugates theorem is just like the irrational conjugates theorem. It basically says, hey, if you end up doing your maybe quadratic formula, hint, hint, and you end up getting something like something plus bi, well, it's also going to have a minus bi as a conjugate. You're going to get 2 different solutions here. I actually want to explore this in example 3 first before I write down the answers to example 2. Here's example 3. We want to create a polynomial function that has rational coefficients, meaning your coefficients have to be whole numbers or fractions, a leading coefficient of 1, and the zeros 2 and 3 plus I. What on earth does that mean? Well, we're trying to write some sort of polynomial, f of x, equals. We know our leading coefficient is going to be 1, so we want it to be 1x to the something power plus something x to the something else plus something x to the something else, so on and so forth, until we get a constant term. How on earth do we do that if we just know some solutions? Well, let's look at the last problem we did. The last problem we did was nice because if we have something in factored form, like this, we can know what the solutions are. But hang on a second, couldn't we work backwards too? Like if I told you our solutions were 0, -2, -2, and -2, couldn't we just realize that this, to make it 0, just has to be x? And for x to be -2, the term should be x plus 2? We can work backwards based on the zeros we're given. Let me give you a little bit of an easier example. Let's say I told you that your zeros were -1, 3, and -2. Couldn't you just write this as x plus 1, because -1 plus 1 is 0, x minus 3, since 3 minus 3 is 0, and x plus 2, since -2 plus 2 equals 0? This is how you can make a polynomial based on your answers. Write out each of the factors, then multiply them together. So let's write out each of the factors of this. We know that the zeros are going to be 2, so what term would I need to put in? What factor would make 2 when it equals 0? Well, x minus 2 will give you a 2. 2 minus 2 is 0. So if one of your zeros is 2, it means that your x should be 2. But what about this one? 3 plus I. Well, what could I put into a factor, add or subtract from 3 plus I to make it 0? Well, here's the key with this one. If you really wanted to make this a 0, couldn't we just subtract 3 plus I? I mean, think about it. 3 plus I minus 3 plus I equals 0. So we can write this as x minus 3 plus I. But just remember, the complex conjugates theorem says that if you have a plus bi, you will also be guaranteed to have the root a minus bi. So if we have 3 plus I, guess what we also have? We also have 3 minus I guaranteed. So then we can write our last factor as x minus 3 minus I. Because we know that 3 minus I is also going to be a solution. You see what we're doing? We're just writing it as x minus our zeros. Now we just need to multiply these together, but this looks insane to multiply together. Remember that when we're multiplying pieces together, we want to multiply the real parts and then the imaginary parts separately. What I'm going to do is I'm going to leave this x minus 2 at the start, and I want us to multiply these things together. So if we have x minus 3 plus I, isn't that just x minus 3 minus I when we distribute the negative. And if we have x minus 3 minus I, isn't that x minus 3 when we distribute the negative? And minus negative I, or just plus I when we distribute it? If I wanted to multiply these two complex terms together, I would have to multiply the x minus 3's as the real parts, and then multiply them with the imaginary numbers. We're going to FOIL this in a very weird way. It's going to take some effort, but we're going to make it there. First things first, what is x minus 3 times x minus 3? Well, x minus 3 times x minus 3 is just x minus 3 squared. But we don't want to leave it like this. If we're doing FOIL, we're doing the first terms, the inner terms, the outer terms, and the last terms. Let's actually multiply x minus 3 out and square it. I'm going to do this off to the side here, just so we can use this as like scratch work. But we should know how to multiply x minus 3 times x minus 3 relatively quickly. X times x is x squared. Negative 3 times x is negative 3x. Negative 3 times x again is negative 3x. And negative 3 times negative 3 is plus 9. So we can write this out as x squared minus 6x plus 9. That's our first multiplication. The rest is actually easier than that first term. Like if I want to multiply the outer terms, like we're required to do for FOIL, I times x minus 3 is just I times x minus 3. If I wanted to multiply the inner terms, what's negative I times x minus 3? Well, it's minus I times x minus 3. And multiplying our last terms, what's negative I times I? That's negative I squared. But hang on a second. As we go to simplify this, doesn't something interesting happen here? I mean, think about it. We end up with a plus I times x minus 3 and a minus I times x minus 3. They cancel out. I x minus 3 minus I x minus 3 is 0. And negative I squared, we know I squared is 1. That's just negative 1. What we end up with is x squared minus 6x plus 9 minus negative 1. In other words, this second factor is, if we roll out our whole factors again, 0 equals x minus 2 times x squared minus 6x plus 9 minus negative 1 is 10. From here, we know how to multiply two polynomials. It's a little bit of elbow grease, but we can multiply these out as well. Try this one on your own, but I'm going to let you know what the answer is to this right away. When you multiply this out, you will end up with x cubed minus 8x squared plus 22x minus 20 as your final answer. I did promise you I would write up one of the solutions to these so you can take a look and try the previous ones out for yourself. So I'll let you know. For this problem up here, you're going to need to use synthetic division, and you're going to need to factor it either using your square rooting method or quadratic formula. You will also probably need to use some grouping in here, if you can. The final answer to this one is going to end up being that x equals -1, -1, 2, and plus or minus 2i. 5 solutions, since this is x to the 5th. With that said, everybody, thank you so much for listening in. I hope you have a fantastic rest of your day.